So in all the different type of windows, all that windows are like they are having a different equation. A particular mathematical expression is going to define that particular window, and once the window is defined, we will be using that window to restrict an infinite impulse response, that is ht of n, to find out the finite impulse response of a particular filter. Okay, so what happens, initially we were having different type of windows, but once we are going to design a system, instead of selecting out of different windows, what we can do is we can have single window, okay, that can replicate all the properties of other windows also. Okay, that we can say like a single window that can generalize all the type of different type of windows in a single expression. Okay, so that is the Kaiser window. So the Kaiser window will be a type of window that will be basically selecting all the different type of windows that we have seen. It can transform their equation to a different type of window functions based on different parameters that is explaining or defining this Kaiser window system. Okay, so that's why we will be dealing with this Kaiser window. So before that, we will see what is the different properties of different type of windows that we have gone through. This is the slide that we have already seen. Okay, so here, okay, so one thing we can see like the main low width. What is the main low width is there? What is its value? That is inversely proportional to m. So as m, that is the order of the filter, is going to increase, this order of the filter will basically change the main lobe width. Okay, so in the practical cases, main lobe width will be high. Okay, but to make this main lobe width, sorry, main lobe width should be low actually, to reduce the transition width. Okay, so if from high to low or low to high is the magnitude response of a filter is going to change from stop band to pass band and pass band to stop band, that should have a quick, or you can say sharp change should be there. Okay, so to have a sharp change, the transition range, the transition frequency range should be minimized. So to have a minimum transition frequency range, we will be requiring the less width of our main lobe. That can be done with respect to the order of the filter. So if we are increasing the order of the filter, then the main lobe width will reduce in all the cases. Okay, so as we are going to select the higher m, this will finally improve our filter designing. Okay, so the increase in window length, so this window length will decrease the transition band. So it says same. If we are going to increase the order of the filter, that will basically decrease the transition band. And the minimum stop band attenuation. So whatever attenuation we are seeing, like the minimum stop band attenuation and the peak side lobe, all these parameters are basically independent of m. Okay, so once we see, so for a window function, whatever window function is there, for that window function, this value of stop band attenuation and peak side lobes are basically independent of their m variable, that is the order of the filter. And here the minimum stop band attenuation has the maximum main lobe width. So there is an opposite trend, like if the main lobe width is increasing in this order, then the peak side lobes are decreasing, okay, in this way. So and both are like, we should be having minimum number of main lobe width, but we are requiring higher number of peak side lobe. So, peak side lobe is in the value of dB, so it should be having a higher degradation. Okay, so to reach these conclusions, we have seen in the previous class also, like how we should be deciding like which window function is going to be used for a particular specification design. Okay, so in the conclusion, we can say if we are going to design a filter with a particular specification, the length of the filter must be high. Okay, the order of the filter must be high for reducing the main lobe width. So, so we should be having higher M value to reduce this main lobe width value, but we cannot reduce this main lobe width or we cannot increase that M value beyond a certain point. That will increase the complexity on our system, basically in terms of hardware requirements. So we should be taking the M value by keeping the specifications into the consideration. Okay, so in this case, a simple approximation to these functions have developed by the Kaiser window. Okay, in terms of zeroth order Bessel function. So here we will be a Bessel function. Okay, a Bessel function. We will see like what is a Bessel function is there, how it is defined. So a Bessel function expression is being used in this Kaiser window to basically approximate all the different functions, okay, window functions in a single expression. By using a single expression, it will be uh, designing, it will be depicting all the properties of different windows. And here, what are the different window, Kaiser window, what it requires, or what is gives, what are the advantages like. Okay, allows ripple, allows certain transition width. As a result, we will be getting uh, different type of, you can say, window functions by changing these values. Okay, so there are different variables, parameters that will be defining this Kaiser window function, and this Kaiser window function will be providing you different functions, window functions, and that can be compared with the all other window functions. We can see like it is going to replicate all other window functions. So we will be uh, only, you can say, in practical applications, we will be basically seeing the Kaiser window. Like Kaiser windows are the windows uh, that will allow us to provide different variables, and these variables will be in terms of the Bessel function. So here, this variables will be finally defining the window function, and these window function can have different properties based on our requirements. So in that Kaiser window function, like all other windows, this Kaiser window is having a function like wk of n that will be equals to I naught into I naught, which is a function of beta, and similarly divided by I naught, that is a function of alpha. So, and this is the case when n is ranging between minus m minus 1 to n minus m minus 1 by 2 to m minus 1 by 2. Okay, so it is defined in case of the positive and the negative direction. So like all other window functions we were defining, okay, the Kaiser window is similarly defined. This is like a non-causal equation. So in that, if n value is ranging between this and this will be the function that is defined. So here I naught and x is called the zeroth order Bessel function. So we'll see like what is basically the zeroth order Bessel function is. We will expand it further. So this is the basic expression of this Kaiser window. Okay, so here in this type of analysis, in this type of window, here the side lobe level, whatever side lobe height is there, that is controlled with respect to the main lobe peak by varying the parameter alpha. So by varying the parameter alpha, that is alpha, based on this alpha value, we can control the side lobe level, okay, or we can say side lobe height and the main lobe width. So this main lobe width and side lobe height will be varying in case of the alpha varying. So once we are changing the alpha, that will be changing the W and the these two parameters that are required while designing any filter. This filter designing will have these two parameters, important parameters. So we should be checking or uh, seeing like it is having a particular range that is according to our specification or not. Okay, and the width of main lobe can be varied by adjusting the length of the filter. Similarly, uh, in the expression, or we can say in the chart, we have seen here different main lobe width are being varied with respect to the M value, that is the order of the filter. So similarly, in the Kaiser window also, we will be having some relation of this width with respect to the M. Okay, so order of the filter will be affecting this value, and but in all other cases, the stop band determination and peak side lobes were basically, you can say, this basically in case of stop band determination, it was independent of M value. Okay, so in Kaiser window, we will be having a variable, a parameter that will be affecting these independent variables, independent values in case of other window functions. So here in case of Kaiser window, we can control the width of the filter by using main lobe width of the filter by using this length, or we call it the order. With respect to the order and length of the filter, we can change the main lobe width as that was in all other window functions. But even here, we can change the value of side lobes that will be giving you the errors. So these side lobes can be minimized by varying the parameter alpha. So there are two different values, parameters that we should be considering. Okay. Okay, so this is a different type of representations, like how we should be representing a low pass filter, high pass filter. Okay, so if a low pass filter is there, its frequency response, the magnitude plot of the frequency response. So this is h of omega. We are giving you the magnitude. So this sign indicates magnitude. So we are going to plot the magnitude of the filter with respect to the frequency. So here, this is like the practical one. So this will be the maximum one, and if delta p is your pass band attenuation, so this can be less than one. So one minus delta p or one plus delta p. So it can have a variation between these two. And if this delta s is the stop band attenuation, so that will be at a particular frequency that is called fs, that is stop band frequency. So this is pass band frequency, and this will the point where cutoff frequency is there. So at cutoff frequency, it will be like point where it will be having the value that is 1 by root 2 of the 1. Okay, so what is the maximum value? That is a is the maximum value. So whatever is the value that is 1 by root 2, that will be your cutoff frequency value. Okay, so this is how the cutoff frequency is defined practically. Okay, so in general, we basically considered passband frequency to the you can say cutoff frequency, but in practical, it should be in between these two. And for our similarly high pass filter, band pass filter, and band stop filter. So these are the specifications that we should be knowing while designing. Like if band pass filter is there, so it will be passing for a particular fixed band, and this is like if band stop is there, so for a fixed frequency range, it will be stopping the signal, or other frequency range it will be changing. So between low to high or high to low, there is no direct sudden change. There is a change, but it is taking some time. It is taking some frequency range in between the change from high to low. Okay, so that middle of this change will be considered the cutoff frequency. All other will be okay in a row. Okay, so we have seen this as the Kaiser window function. So in that Kaiser window function, we will be defining these alpha and beta values. Okay, so this alpha and beta values can be defined like this. Beta value is defined by, okay, so this beta value is defined by alpha into 1 minus 2n by m minus 1 to the power 2 to the whole power 0.5, that is 1 by 2. Okay, so this is how the beta value is defined. That is the part of numerator. So this is the part of numerator of your window function. Similarly, we will see the denominator too, but before that, what is Bessel function, like how the Bessel function is defined. If I naught into x is a Bessel function, so how the expansion of this Bessel function should be taking place. So the Bessel function expansion is given like, if I naught x is there, that will be 1 plus summation k equals to 1 to infinity 1 by factorial of k into x by 2 to the power k to the whole square. Okay. So this is seems to be quite complex, so we will expand it further. So it will be like 1 plus 0.25 x square divided by factorial 1 square plus 0.25 x square. Okay, so the power here is like 2. It will be okay. So this is 1 and this is 2, and similarly it will be increasing with respect to the order of this value. Okay, so this is going to increase once we are going to have expansion of further terms. So this is how the value should be increasing. So based on the beta value or the alpha value, we will not be expanding in all the cases. Okay, we will be just finding out the alpha value and beta value to finally get the window function. We should be getting some values of it before the that will be having a significant you can say contribution. If the values are less, we will be neglecting these values, so we will be only considering the significant values only. Okay, so this is how the Bessel function is defined. Next is uh, also we will be having in the, suppose low pass filter is there. Okay, so in case of low pass filter, it will be having, this is one, then it is having AP and AS. So AP and AS are, it will be in dB. dB value we have seen, like it will be in dB. Otherwise it will be delta A, delta A, sorry, delta P, sorry, delta P, that is pass band, delta S as stop band attenuation. So once we will be having delta A and delta, sorry, delta P and delta S by the specification, we will be finding out that is AP, or we call it pass band attenuation and stop band attenuation. So out of these, we will be finding out these two values. So after finding these two values, we will be using it to get all other values. Okay, so before that, we will be finding this two, and here a delta value is used. So that will be we will see later. And here the transition frequency band will be given by changing the frequencies, like whatever omega s is there, omega p is there. So difference will be in terms of radian per second, and if it is delta, sorry, fs minus fp, that will be in hertz. So this is your transition band. So transition band, or we can say range of frequencies, will be called as the bandwidth. So it is transition bandwidth. And similarly, delta P and delta S as they are defined. So based on that, delta S and delta P, we will be finding this. Okay. So if in the previous representations, we have seen like one is their magnitude, and before that, in the below side, we have taken delta P as the passband attenuation. Okay. So but here it is like two variations are given. One, it can be in positive direction, or even it can be in negative direction. So the passband attenuation in terms of dB will be given like A into 20 log 10 1 plus delta P divided by 1 minus delta P. Okay, that we will be getting the dB value for passband. Similarly, and the stop band, it will be this only. So here in passband, it is getting the ripple. It is basically uh, uh, indicating like in passband, it is having a ripple, so it can be positive and negative. So this is how the actual analysis would be taking place to have a more accuracy. Okay. So once we have specified the ripples, whatever ripples are there into the passband and stop band attenuation, so then we will be finding out the ripples that will be minimum of these two. So whatever minimum value is there, or whatever minimum value is there, we should be uh, taking that is satisfying both the cases. Okay, so we will see it later while performing the numericals also. Okay, so how the design specifications should be given for designing. So these are like if design specification is to be given for designing a filter. So this is how the different values are to be required while designing a different uh, filters by using a Kaiser window. So what type of filter is there, that should be given. Okay, pass band stop band attenuation frequencies in hertz if it is given. Okay, that should be FP, FS for low pass and high pass. Similarly, if it is band pass and band stop, it will be having two different uh, frequencies. If it is band pass, it will be having two frequencies, that is FP1 and FP2. Similarly, if it is band stop, it will be FS1 and FS2. Okay. So pass band ripple and minimum stop band adjustment in positive decibels. So in positive decibels means it is basically just indicating making it to be in positive values. Okay, so whatever values we are getting here, if it is negative, we will be making it to a positive value. Okay, and sampling frequency we need, that is F. Okay, and order of the filter. So these are the different type of parameters that will be requiring for designing filter by using the Kaiser window. Okay. So if less specifications are given, so we will first go for searching of these values. Okay. So M values, F value, that is sampling frequency, uh, pass band attenuation and stop band attenuation, that will be in terms of positive parts, positive values, and the frequencies, whatever pass band and stop band frequencies are there, that we should be having. So once we have all the design parameters, we will be following a step by step process for designing the Kaiser window. Okay. For designing any filter, FIR filter by using the Kaiser window. These are the basic steps. So the first step we should be having is we need to define a delta value, attenuation. Okay. So suppose an attenuation is there. So in the frequency magnitude response of the magnitude response of the desired filter. So if this is the one value, okay, this one is one, and there is a variation between one, so it is going high and minimum, and this is the stop band value. Okay, so this is the stop band attenuation value. So out of these two, which one is minimum, that will be used for defining the attenuation value. So like suppose if it is 0.02 and it is 0.01. Okay, so if we are considering minimum of these two, means we are considering the maximum attenuation. Okay, targeting this. So when we are going for designing, what we should be doing is whatever is the minimum value out of these two, delta P and delta S, we will be going for designing that range or that specification that will be considering all the parameters. Suppose if we are considering this for designing a filter, okay, this delta attenuation is to be considered 0.02. If we are considering 0.02 for designing a filter, then it is already including 0.01. Even if a filter is there that is having a specification having attenuation of 0.01, it is being considered here. If we are going for designing the worst case, it will definitely satisfy the below value of the worst case. Okay, so that's why when going for selection of the delta, that is attenuation, this is basically the attenuation. So what is the attenuation in the passband and what is attenuation in the stop band? Out of these two, whichever is the minimum, that will be considered as the delta value, that is attenuation. Okay, so once we know the attenuation, okay, once we know the attenuation, these attenuation values will be further used. dB value of stop band attenuation and pass band attenuation, okay, that is in the dash means it is in positive value. Okay, it is positive value. So if this attenuation values are given into the question, then from there we have to find out the delta S and delta P by using these formulas, and then we have to find out the delta. Once we know the possible attenuation and stop band attenuation, from there we will be calculating delta P and delta S, and from there we will be finding out the delta, that is the attenuation. Okay, so this is the first step. Second is we need to find out AS, stop band attenuation. That will be in terms of the values that we have defined previously. So from there, we will be calculating the AS value. Once we know the AS value, with respect to that is AS value, what is the range of this stop band attenuation value in terms of dB, that is below 21. So then the value of alpha, that is this alpha value is the denominator part of your Kaiser window function. Okay, so this alpha value, because in Kaiser window it was like Bessel function beta divided by I naught alpha. Okay, so this alpha value that should be the function of Bessel function will be find it out by using this expression. So this is the expression for finding out the alpha value. So here if AS value we know, so from there AS value, what is the range of AS value? If it is greater than 50, we will be using this as the expression. If it is between 21 and 50, we should be using this expression. And similarly, if AS value attenuation is less than 21, then we will be making alpha is equals to 0. So this is how the alpha we should be finding. And one more parameter is there, that is called the parameter D. So this D parameter will be defined as an expression defined by this. These values we have calculated. So the F value. So once we know the D value and alpha value, so our main motive is to find what is for designing the filter. We should be knowing the M value, because in the question it will not be giving you the M value. If it is given the M value, we can use that directly. But in while designing the Kaiser window, it will not be giving you the M value as usual in the previous window functions. It was already given like the order of the filter is this. But here in this case, it will be giving you the specification in terms of the attenuation and the frequency. Okay, so it will be in terms of delta P, delta S, and frequencies. So these values will be given. So based on these values, we have to find out the value of M. What is the order of the value, order of the filter? We should be finding out this M value, and then we will be defining the filter. Okay, the window function will be defined with respect to the specifications itself. But in all other cases, like window functions were fixed for all type of designing. But in this case, we are going to find the window function with respect to the value of the order, whatever order of the filter is there, and whatever other specifications in terms of attenuation and frequency it is given. So the fourth step is this, that we need to find out the D. Once we have found out the D, we will be getting the order of the filter, and this order of the filter should be greater than or equal to FD. Okay, so FD is the frequency difference that we have, passband, stop band, and passband. Okay, higher and lower, divided by delta F. Sorry, this FD is F. Sorry, this F is your sampling frequency actually. and D is this value that we have calculated. Okay, D, and delta F is your, if it is F, it will be in terms of F, so Fs minus Fp. So stop band frequency minus the pass band frequency, or you can say the higher frequency minus lower frequency. Okay. So this will be this plus 1. So we should be selecting m values that should be greater than or equal to fd divided by delta f plus 1, and this m value should be odd, so that will be the lowest odd value of m. So because while designing filters, we are basically going to use this 1 minus m minus 1 divided by 2. Okay, so all the filters are defined in terms of this window functions. So we will be considering the odd values of m only. So whatever the lowest value of odd will be coming out from this formula, that will be your order of the filter. So once we have the order of the filter getting, from there we can get the window function. Okay, so window function we can define. So once we know the window function, and we will be having the hd of n. So hd of n we will be defined by this, the frequency response. We will be taking the inverse Fourier transform to find out the hd of n. So by multiplying hd of n into the window function, that we will be getting the impulse response of the modified filter. So whatever modified filter we were going for designing, that will be your h of n, that will be given by this. Okay, and this will be similar because this will be defined for n is equals to this. So this is because of the uh, window function, because window function is defined in this range only. So our uh, impulse response of the desired filter we will be defining this way. So once we know the h of n, similarly we can get the h of z. Okay, and once we know the h of z, suppose we need to calculate the magnitude and frequency, then also we can calculate the magnitude and frequency from the previous function. So in the previous way, whatever frequency response we were calculating, the same way we can calculate the frequency in phase response. Okay. So all the steps are same. The only step is different is here we are not having a fixed window function. That fixed window function we have to design first. Okay, so this fixed window function we have to design with respect to our specifications. Okay. So in all other cases, like the window functions that we have gone through, it is having the fixed window function, and whatever is, m value is given with respect to that, is it's going to further the direct designing. Okay, but in case of Kaiser window, we will be going to find out that m value that can be the optimized value. We can say we can find the m that is the order of the filter, which is an optimized value for including all the specifications given into the question. Okay, so whatever specifications are given, that incorporating that specification, we will be finding out the minimum value of m that is possible, because once we know the minimum value of m, okay, so this minimum value of m that is going to satisfy the condition, we can reduce the complexity of the circuit. Okay, we can call it like complexity, or even we can say like if m is higher, we can we can require the higher hardware. Okay, but if we are reducing the order of the filter, we will be basically reducing the hardware requirement, so we can have a more complex design. So this is how this Kaiser window is more helpful in terms of designing of the FIR filters. These are basically the expressions, so generalized expressions for stop band, pass band, low pass filter, high pass filter, FIR filters. So these are generalized expressions that if a given system is there, then this will be a your generalized frequency response or you can say impulse response. They are like hd of n. So it is just by considering the whatever hd of omega is given. So this is like after taking the inverse Fourier transform, it will be giving you the uh, filter response, and these are the generalized one we will be seeing while seeing the numericals. Okay, so this is the comparison of different window functions. Okay, but in case of Kaiser window, we can see like the maximum magnitude of the side lobe with respect to the peak of main lobe is variable, and that is given by the parameter alpha. So here this is not a constant value, or that is not an independent value, but in Kaiser window we will be getting this uh, maximum magnitude of side lobes that will be defined in terms of alpha. So we can tune these values. So based on our requirement, we can tune the side lobe maximum magnitudes, okay, with respect to the changing of alpha parameter. In terms of the magnitude of side lobe, here the magnitude of side lobe decreases with increase in the omega value, that is the frequency value. If we are going to increase the frequency, it is going to decrease. So we have seen what is the frequency response we get. So this is the maximum one, and after that it keeps on decreasing as the frequency is increasing. This is along the omega. So as the frequency is increasing, it is going to decrease. So the same way we will be having that once we are going to increase the side lobe magnitude is going to decrease. And also the minimum stop band attenuation here is also, in case of Kaiser window, is not a constant value, but it is attenuation is a variable and depends on the value of alpha. Once we are going to change the alpha value, it will be changing. Okay, so here we can see like in window Kaiser window, we are having more power to optimize the FIR filter design. Okay, so this Kaiser window will be providing you the optimized, we can say, optimized FIR filter. Okay, so that's why this Kaiser window is considered to be the generalized one that is going to depict all other window functions. Suppose we are going to plot the window function, magnitude of the window function with respect to the different n values. Okay, so suppose different n values are there, 0, 5. So this is 20. If we are going to change the value of alpha into the Kaiser window, then what type of window we will be getting? We will see that by using the different value of alpha. So suppose we are going to change the alpha value, and if alpha value is 0, this will be the window function. The magnitude of this window function will be constant, 1 will be there. So okay, this is like suppose this is 1. Okay. Similarly, suppose our alpha value is coming out to be 2, or we can leave 3. So this is just for an illustration, like how the alpha value of the Kaiser window is going to depict all other different type of windows. Okay, so these are not the exact values. Okay, so but there are some slightly changed values that depends on the order of the filter. So that is not. So suppose if this is coming out to be for order m is equals to 21. So this is an example given having a sample of 0 to 20 samples, and it is having an order that is 21. Then this will be coming out like if alpha is 0, then that will be depicting you the rectangular window. Okay, so this will be giving you the rectangular window. Alpha is equals to 0, it is giving you out the rectangular window. Similarly, if we are going to change alpha is equals to 1 value, then okay, so this is like alpha is equals to 3. If alpha is equals to 3 is there, this will be the type of window function. So what is this window function is? Yes, anyone? So this is your window function that is defined having some magnitude. So this magnitude could be like 0.08. So this is instead of starting with 0, it is starting with a magnitude. So this is defining basically a Hamming window. This is Hamming window. So this Hamming window is also called raised cosine window, because instead of starting with 0, it is going to start with a particular value that is 0.08. That's why it is called raised cosine window. It is being raised from 0 to 0.08 value. Okay, so that is called raised cosine. So if we are going to change the alpha value to 3, it is going to have a depiction of Hamming window function. Similarly, if we are going to change the m value, the alpha value to another value, that is suppose it is 6. So in that case, the window function that we will be getting is so this will be for alpha is equals to 6. So for alpha equals to 6, it is having a window function that is similar to a Hamming window, but it is starting with 0 and also it is ending at a 0 value. Okay, so this is the window that is called Hamming window, because in Hamming window, the first function is like 0.5 minus 0.5 cos function. So if cos is 0, if it is cos is 0 or cos is the maximum 20, it will be again giving out the one value. So 0.5 minus will be equals to 0. So it is giving you starting with a 0, it will be ending at the 0. So this will be giving you out the Hamming window. Okay, so this is a basic idea to understand the Kaiser window. So in the Kaiser window, once we are going to change the value of alpha, we are going to change the different type of window. Initially it was rectangular window. It can give you the Hamming window also. Once we change the alpha to 6, it can give you the Hamming window also. Okay, so this is how the Kaiser window depicts all other windows. So this is the main advantage of using the Kaiser window. Okay, and also it is having a variable. Uh, it is also having a variable that is alpha and beta that is going to change the side lobe height and the main lobe width. So we are having a control of these two variables. So that's why it is providing you the more optimized filter that we are going to design.